Every textbook gives Earth the same ending. 5 billion years from now, when a dying sun finally swallows the planet whole. That ending may be wrong on both counts. New research suggests Earth might actually escape being swallowed entirely. But here is the part almost no one tells you. Long before that final chapter ever arrives, something else runs out first. Scientists have now calculated the precise moment Earth's breathable air begins to fail, and the number is nowhere near 5 billion. It arrives closer to 1 billion years from now, a death sentence already ticking forward beneath your feet with every year the sun grows brighter. Tonight, we uncover the real date Earth actually dies, and why that number is so much closer than anyone has ever told you. If a question this large deserves an hour of quiet company, a like and a subscribe genuinely help keep these evenings coming, more than any of us really need to say out loud. Get comfortable and let the night take over. In 3, 2, 1, lift off. There was a time, not so very long ago, in the life of this planet, when people set their whole days by the sun without giving it a second thought. Farmers rose with it, ate supper as it set, and marked the turning of the seasons by how high it climbed at noon and how long its light lingered into evening. Long before anyone understood what the sun actually was, entire cultures built monuments to track its path across the sky with such patient precision that some of those structures still align perfectly with a solstice sunrise today, thousands of years later. It never seemed to ask anything of anyone. It simply rose, warmed the fields, and set again, day after day, in a rhythm so steady that whole civilizations built their calendars, their harvests, and their sense of order in the universe around the plain assumption that the sun would always behave exactly as it had the day before. That assumption, it turns out, was never quite true, and it becomes less true with every year that passes. The sun is not a fixed lamp hung in the sky, burning at some constant, unchanging rate until the day it simply switches off. It is, by any measure that matters to a planet, the single largest object anyone born on Earth will ever lay eyes on, a sphere so vast that roughly 1 million Earths could be packed inside it, with room left to spare, holding within its gravity every planet, moon, asteroid, and comet in the solar system combined, all of it together amounting to only a small fraction of the sun's own mass. Something built on that scale does not change on any timetable a person could reasonably picture. It changes on a timetable measured in hundreds of millions and billions of years. But it does change steadily, aging the way anything with a finite supply of fuel ages, and every stage of that aging reaches down and touches this planet in ways most people never stop to consider. Somewhere in that slow, ongoing change lies the real answer to a question almost everyone assumes they already know the answer to. When, exactly, does Earth actually die? Ask that question at a dinner table, and you will likely hear some version of the same story. Someday, billions of years from now, the sun will swell into something called a red giant, growing enormous, swollen, and deep red, and it will finally reach out and swallow the Earth whole, the way an incoming tide closes over a sandcastle built too close to the water at the end of a long summer afternoon. It is a striking image, passed down through documentaries and textbooks alike, and it happens to be built on something real. Stars, very much like our own sun, do eventually leave behind the long, stable middle chapter of their lives, and in their final act, they do swell to sizes that reach toward the orbits of the innermost planets. The core, having spent billions of years converting hydrogen into helium, eventually runs low on the fuel that held everything in balance, and gravity, unopposed for the first time in the star's long life, begins to win. The core contracts, and grows hotter still, while the outer layers respond by ballooning outward to enormous size, cooling as they expand and turning that familiar yellow-white light into a deep smoldering red. Astronomers can point a telescope at stars living through exactly that phase tonight. Aldebaran, the reddish eye of the constellation Taurus, is one such star, a giant some 40 times wider than our Sun, already living the very future our own star is heading toward. And it is far from alone in the night sky in that regard. But two things about that familiar ending deserve a much closer look, and both of them matter more than the popular version ever lets on. The first is timing. The event most people picture, a giant, swollen sun bearing down on the inner solar system, sits roughly 5 billion years in the future, a span of time so large that the mind has almost nowhere to put it. Nothing in tonight's story should be mistaken for an urgent warning about tomorrow, or next year, or any year within reach of memory or planning. This unfolds on a timescale belonging to the planet itself, not to any single person standing on it, and most of what follows will still hold true for the entire span of human civilization so far, many times over. The second point worth reconsidering is a question that has only recently been reopened by scientists studying the physics of dying stars in far greater detail than ever before, a genuine, live debate we will return to later in this video. Whether the Earth is actually swallowed by that expanding sun at all, or whether, against all popular expectation, it might slip free. For tonight, set that distant ending aside. It is not, despite how often it gets told, the part of this story that should hold your attention first, and it is certainly not the part that explains what is actually happening to this planet right now, this evening, while you listen. Because long before the sun ever becomes the swollen giant of popular imagination, something quieter, closer, and far less dramatic is already unfolding, a process with no single dramatic moment and no obvious warning sign, one that has been running patiently in the background since long before there was anyone here to notice it. The sun that rises tomorrow morning will be, in a small but genuinely measurable sense, brighter than the sun that rose today. Not by any amount your eyes could ever detect, not by any amount that will change a single sunrise in your lifetime, or in the lifetime of your grandchildren, or theirs after them. But it is happening, gradually, the way a person's hair slowly turns silver over the decades without any single day ever marking the change. And it has been happening for the entire 4.5 billion years the sun has existed. At its heart, the sun is a furnace held together by its own enormous weight, converting hydrogen into helium deep in its core and releasing, in that conversion, the light and warmth that reaches Earth roughly 8 minutes later as ordinary sunshine on an ordinary afternoon. As that process continues, year upon year, the makeup of the sun's core very gradually shifts, growing slightly denser and slightly hotter, and, as a direct consequence, burning slightly brighter. None of this is guesswork or rough extrapolation. For several decades now, a series of satellites in orbit high above Earth's atmosphere, free from the interference of clouds and air, have been measuring the sun's total output with remarkable precision, watching for fluctuations far too small for any instrument on the ground to reliably detect. Stitched together, decade after decade of that orbital data confirms the same slow, steady climb predicted by the physics of an aging star. Scientists who study the sun's long history have put a number on that gradual brightening, an increase of roughly 1% every 100 million years. It is a small number in any single stretch of time, and an enormous one across the whole of the sun's life. Today's sun is already close to 40% brighter than the faint, young sun that first warmed a newly formed Earth, and its output shows no sign of leveling off. Astronomers have a name for the long, stable chapter of a star's life the sun is living through right now. They call it the main sequence, the extended middle period, when a star quietly burns hydrogen in its core, shining with a slow, steady patience that can last for billions of years before anything more dramatic begins. The sun has already spent something on the order of 4.5 billion years in that chapter, with perhaps 5 billion more ahead of it, before the fuel finally runs low enough to force the kind of change described a moment ago. Everything discussed so far, the slow 1% brightening, the gradual climb since the sun's youth, belongs entirely to this quiet, ordinary middle chapter. None of it requires the dramatic ending to arrive first. This is the detail almost entirely missing from the popular version of Earth's ending, the one built around a swollen red giant devouring the inner solar system. That dramatic final scene, if it happens the way it is so often described, is the very last page of a very long book. Long before the sun grows large enough to threaten Earth's orbit, its ordinary, unglamorous, everyday brightening, the same kind happening again at this very moment, is already quietly rewriting the terms under which life exists on this planet. It is not a future event waiting patiently to begin. It has already begun, and it began a very long time ago. It took a very particular kind of scientific patience to turn that slow background fact into an actual number, a genuine answer to the very real question of how much longer Earth's present, breathable atmosphere can be expected to last. That work belongs chiefly to a scientist named Kazumi Ozaki, an environmental scientist at Toho University in Japan, working closely with Christopher Reinhard, a climate and biogeochemistry researcher at the Georgia Institute of Technology in the United States. Their collaboration was carried out under a NASA research program built specifically to study what allows a planet to support life in the first place, and, just as importantly, what eventually brings that support to an end. Ozaki and Reinhard did not set out to imagine some distant cinematic catastrophe. What they built instead was closer to an enormously patient accounting exercise, a model tracking the sun's slow brightening alongside the chemistry of Earth's oceans, air, and rock, run not once, but several 100,000 times, each run allowed to vary slightly within the honest uncertainty of Earth's own geology and biology. The question guiding all of it was almost startlingly plain, given everything currently understood about this planet and the star it orbits. How much longer can Earth's atmosphere actually be expected to hold together in a form capable of supporting the kind of life we recognize? We will return to what they found, because it stands among the more sobering figures produced by modern science. For now, what matters most is the method itself, because it points directly toward the true source of this story, a mechanism far older and far stranger than most people would ever think to blame for anything at all: the ordinary rock beneath your feet. That kind of repetition, running the same model hundreds of thousands of times, is not excess for its own sake. Earth's climate and biological history carry real uncertainty within them, exactly how quickly certain chemical reactions proceed, exactly how the deep interior of the planet exchanges material with its surface over vast stretches of time, details that cannot be pinned down with total precision from any single measurement. Running the model that many times, each pass nudging those uncertain details slightly differently, allowed Ozaki and Reinhard to report not a single, falsely confident date, but a genuine range, a most likely answer bracketed by real, acknowledged uncertainty on either side, precisely the kind of honesty any careful scientist owes to a question this large. The tool they built for this purpose links together two kinds of modeling that do not always get combined so carefully. One tracking the biological and chemical processes governing Earth's atmosphere and oceans, the kind of modeling more commonly used to study climate change on far shorter timescales, and another tracking the sun's own long-term evolution as a star, the kind of modeling astronomers use to understand stellar aging generally. Marrying the two required, treating Earth not as a fixed backdrop against which the sun simply changes, but as an active participant, one whose own biology and geology talk back to the star above it in a continuous, centuries-spanning conversation. Toho University sits in the city of Funabashi, part of the Greater Tokyo area, a research institution with a long-standing focus on environmental science, while the Georgia Institute of Technology, thousands of miles away in Atlanta, has built a well-regarded program studying how planets and their atmospheres change together over deep time. The distance between those two campuses, half a world apart, says something about how modern science actually gets done. Patient collaboration stretched across oceans and time zones, all of it aimed at answering a single, carefully framed question about the air over our own heads. Most people, asked what keeps a planet's temperature in check over long stretches of time, imagine something mechanical, almost like a thermostat mounted on a wall, built, installed, and monitored by someone. Earth's real thermostat looks nothing like that at all. It is woven into the plainest, most overlooked process in the natural world, the simple business of rain falling on stone, and it has been quietly regulating this planet's temperature for nearly the entire span of Earth's long history. Here is how it works, described as plainly as possible. Rain falling through the air picks up a small amount of carbon dioxide as it descends, turning very slightly acidic in the process, not unlike the faint sourness of a glass of soda water on the tongue. When that rain lands on certain kinds of rock, especially the silicate stone that makes up much of Earth's crust, it slowly dissolves a tiny portion of that stone through an ordinary chemical reaction, one that pulls carbon dioxide out of the surrounding air and carries it, dissolved, down through rivers and streams toward the sea. There, across enormous stretches of time, that carbon becomes locked away in the shells of tiny sea creatures and in the quiet sediment layers building endlessly across the ocean floor. Some of that ancient, captured carbon is not hidden away at all. It stands in plain sight, visible for miles out at sea. The white cliffs of Dover, rising pale and startling along England's southern coast, are made almost entirely of chalk, the compressed remains of countless microscopic sea creatures that pulled carbon out of an ancient ocean and locked it into their shells millions upon millions of years ago. Every visible layer in those cliffs works like a page in a ledger, a record of carbon that once drifted freely through air and water, now sealed permanently into stone. Multiply that single, visible formation by every similar deposit resting quietly on ocean floors around the world, and you begin to sense the true scale of the process Earth has relied on to keep itself livable for so long. Every river carries some trace of that same process out to sea, whether it's the Mississippi winding down through the middle of a continent or a narrow mountain stream barely wide enough to step across. Water is, in a very real sense, patiently disassembling the continents one raindrop at a time, and has been since long before there were riverbanks anyone could name. Most of what it carries away is invisible, dissolved so thoroughly that nothing looks different to the eye. But the chemistry within that invisible cargo does exactly the work described a moment ago, drawing carbon dioxide down out of the sky and walking it quietly toward the ocean floor. The remarkable part is what happens when the planet warms. Warmer air holds more moisture, rainfall increases, and that increased rainfall speeds up the very weathering process just described, drawing carbon dioxide out of the atmosphere at a faster pace. Less carbon dioxide in the air means less heat trapped near the surface, and the planet cools back down, which in turn slows the rainfall and the weathering, easing the rate at which carbon dioxide gets pulled from the sky. Without any machinery at all, this becomes a self-correcting loop, one that has kept Earth's temperature within a livable range through ice ages, warm interludes, wandering continents, rising mountain ranges, and, most importantly, for tonight's story, through billions of years of a star that has never once stopped growing brighter. Geologists studying Earth's deep past have found traces of this loop working at extraordinary scale. Many researchers believe that the slow uplift of great mountain ranges, such as the Himalayas, beginning tens of millions of years ago, exposed enormous amounts of fresh silicate rock to rainfall for the first time, accelerating weathering across the planet and contributing to a long, gradual cooling trend visible in the geological record. It remains one leading hypothesis among several, not a settled certainty, but it offers a vivid, physical illustration of just how much influence this quiet chemical process can carry across the whole of a planet's history. None of this happens quickly by any standard a person could reasonably apply to their own life. A single raindrop dissolving a single grain of exposed stone accomplishes almost nothing on its own. It is only the staggering repetition of that same small event across every mountainside and riverbed on the planet, over spans of time reaching into the hundreds of thousands and millions of years, that adds up to anything capable of nudging a planet's entire climate. Earth has never been in a hurry about any of this, and it is not about to start now. Much of what scientists know about this history comes from drilling, quite literally, into the seafloor itself. Research vessels, operating as part of long-running international ocean drilling programs, have spent decades pulling up core samples from beneath the ocean floor, cylinders of compacted sediment reaching down through layer after layer of accumulated time, each layer a further page in the same ledger described a moment ago. Reading those cores the way a person might read growth rings in an old tree lets scientists reconstruct, with genuine confidence, how the planet's carbon budget has shifted across tens of millions of years. Picture it a simpler way, if it helps to hold on to. Imagine an old farmhouse kitchen with a wood stove standing in the corner, the kind that never needed a thermostat at all, because a careful hand simply added another log when the room turned cold and let the fire die down when the kitchen grew too warm. Earth's weathering cycle plays that same quiet, careful hand, log after log, for stretches of time too long to comfortably picture, without any hand present at all, run purely by chemistry, rainfall, and patience. For most of Earth's long history, this arrangement worked beautifully, almost suspiciously well. As the young sun, fainter than today's, slowly brightened across the early chapters of Earth's story, the weathering cycle simply adjusted to match it, quietly drawing down slightly more carbon dioxide to compensate, holding the surface within a range where liquid water could persist, and, eventually, where life could take hold and spread across the planet. Scientists sometimes point to this remarkable stability as the very reason Earth has enjoyed billions of years of a relatively temperate climate while orbiting a star that has never for a single day stayed exactly the same. But every self-correcting system carries a hidden assumption inside it, and Earth's carbon thermostat is no exception to that rule. The entire arrangement depends on there being enough carbon dioxide left to draw upon in the first place. A wood stove that has already burned through the last log in the house cannot simply keep adjusting to a cold room, no matter how carefully the hand tending it wishes otherwise. And a planet whose weathering cycle keeps pulling carbon dioxide out of the sky, decade after decade, era after era, in order to keep pace with a star that only ever grows brighter, is, without anyone ever designing it this way, slowly spending down a resource it has no real means of fully replacing at the same pace it removes it. This is the shape of the irony sitting at the very center of tonight's story, and it is worth sitting with for a moment before moving further into it. The very mechanism that protected Earth's climate for billions of years, the quiet, patient chemistry of rainfall and stone that allowed this planet to remain hospitable across so much of its long history, is the same mechanism that will, eventually, help bring that hospitality to a close. Nothing needs to arrive from beyond this world to end the one we know. No comet, no impact, no failure of any single dramatic system, just the ordinary, faithful continuation of a process that has been working exactly as it should since long before the first simple cells appeared in Earth's ancient oceans. Oxygen makes a particularly compelling signal to search for in the first place, precisely because it should not, by the ordinary rules of chemistry, remain abundant in a planet's atmosphere for long. Left alone, oxygen reacts readily with rock, with metal, with almost anything it touches, and should gradually disappear from the air within a relatively short stretch of geological time. Finding it in real abundance, the way it exists in Earth's atmosphere today, suggests something is actively replenishing it, faster than ordinary chemistry can remove it. On Earth, that something is the vast, ongoing work of photosynthesis, carried out quietly in every forest, every meadow, and every patch of ocean, covered in floating algae, day after day, without pause. An oxygen-rich atmosphere, in other words, tends to mean a living one. It is worth understanding, too, why a question this specific to one planet ever caught the attention of a NASA research program in the first place. Ozaki and Reinhard were not working in isolation, curious only about Earth for its own sake. Their research sits inside a much larger effort to understand what a living world actually looks like from a great distance, the kind of distance separating Earth from the many thousands of planets now known to orbit other stars. Telescopes built for exactly that purpose now sit in orbit, far from Earth's own atmospheric shimmer, patiently measuring the faint chemical fingerprints hidden in starlight that has passed through a distant world's atmosphere on its way to a waiting detector. It is painstaking, deliberate work, the kind that can take years to produce a single confident answer about a single distant planet. When astronomers search those distant worlds for oxygen in their atmospheres, hoping it might signal the presence of life, they are leaning on an assumption well worth testing carefully, that an oxygen-rich atmosphere is a stable, long-lasting feature of a living planet, one likely to remain in place for as long as that planet remains alive. Earth's own future, as strange as it sounds, turns out to be the best laboratory available for testing that very assumption. There is something almost humbling in that reversal. For generations, scientists have pointed their instruments outward, scanning nearby stars for any hint of a world resembling our own, treating Earth as the fixed, dependable answer key against which every distant discovery gets measured and judged. And here, quietly, sits a very different question, one that uses Earth not as the answer but as the unknown, asking how long this particular answer key will even remain valid before it, too, needs revising. The fixed point, sitting at the center of humanity's search for life elsewhere, it turns out, was never quite as fixed as it looked. Scientists have a familiar term for the band of space around a star where a planet can hold liquid water on its surface, neither so close that oceans boil away, nor so far that they freeze solid. They call it the habitable zone, sometimes described more casually as the Goldilocks region, and Earth has always been held up as the model example, the porridge that came out just right. But a zone, on its own, only describes geography. It says nothing about how long any particular world sitting inside that zone gets to keep enjoying the conditions that make it hospitable in the first place, and it says nothing at all about a star that, however slowly, never stops shifting the very boundaries of that zone as it ages and brightens. This reframes something worth carrying forward into everything still to come tonight. When people speak of a habitable planet, they almost always mean it as a place, a location sitting at the right distance from the right kind of star, warm enough for liquid water and cool enough to keep it from boiling away. That is true, as far as it goes, but it leaves out something essential. Habitability is not only a place, it is also a duration, a window of time with a beginning and, inevitably, an end, and the length of that window depends on exactly the kind of slow planetary bookkeeping Ozaki and Reinhardt set out to calculate. A planet does not simply become habitable and remain that way forever, immune from its own history. It becomes habitable, stays that way for a finite stretch, shaped by its star and its own geology working in tandem, and then gradually stops. So the true story of Earth's ending does not begin with a swollen, furious sun bearing down on the inner solar system, however vivid that picture remains in the popular imagination. It begins here, quietly, with sunlight arriving fractionally stronger than it did 100 million years before, with ordinary rain falling on ordinary stone, and with a planet's own chemistry faithfully, tirelessly continuing to do exactly what it has always done. What Ozaki and Reinhardt wanted to know was simple enough to ask, and almost unbearable to answer. Very real precision, given a star that only brightens and a thermostat with a limited, dwindling supply of what it depends on. How long does Earth actually have left, with air that anyone alive today would still recognize as breathable? It is a strange kind of question to sit with, one without much precedent in ordinary experience. Nations calculate budgets in years. Geologists calculate them in ages and epochs stretching into the millions. This calculation runs further still, out toward the edge of what the word billion can even begin to convey. And yet it arrives at something startlingly concrete, not a vague sense of someday, but an actual number, worked out, with the same rigor any bridge engineer or structural inspector would demand before signing off on something meant to stand for generations. That figure exists now. It has been calculated, checked, and calculated again. And it sits far closer on the calendar than almost anyone assumes. The number itself, once you finally hear it, has a way of rearranging everything that came before it. Ozaki and Reinhardt's model, run and rerun across several 100,000 separate calculations, converged on a mean estimate of 1,080,000,000 years from tonight, with a stated uncertainty of roughly 140 million years in either direction, not 5 billion, not some safely distant number comfortable enough to set aside and forget. 1 billion years, give or take, before Earth's atmosphere stops being the kind of atmosphere that could keep something like you alive. Set the two figures side by side for a moment. 5 billion years marks the earliest point at which the Sun might grow swollen enough to threaten Earth's orbit. 1 billion years marks the point at which the air itself, quietly and without any single dramatic event, stops being breathable in the way every living thing on this planet currently depends on. The gap between those two numbers is not a rounding error. It is roughly 4 billion years, an entire second history of the solar system's remaining lifetime, folded into the space between when the air runs out and when the more famous, more cinematic ending was ever expected to arrive. There is another way to hold this number that might land more clearly than the count of zeros alone. If the entire remaining stretch of the Sun's stable, ordinary life, the whole 5 billion year span still ahead of it, were compressed into a single 24-hour day, the point at which Earth's air stops being breathable would arrive only a little past 5 o'clock in the morning, with the overwhelming majority of that long day, the entire remaining morning, afternoon, evening, and night that followed, still stretching out ahead, entirely uninhabited by anything resembling the audience of tonight's program. It helps, before going further, to remember just how strange and hard won the air around you actually happens to be. For roughly the first half of Earth's entire history, there was essentially no free oxygen in the atmosphere at all. The air of that ancient world would have been unbreathable to anything alive today, rich in methane, and largely without the protective layer of ozone that currently shields the surface from a good portion of the Sun's ultraviolet light. Oxygen only began accumulating in earnest once certain photosynthetic microbes, tiny organisms living in ancient seas, perfected a chemical trick for splitting water using sunlight, releasing oxygen as a kind of waste product in the process. That waste product built, slowly, increment by increment, molecule by molecule, over hundreds of millions of years, into the rich, breathable atmosphere. Every living thing above the microbial level now depends on entirely. What Ozaki and Reinhard describe is, in a very real sense, that same story told in reverse. The slow unbuilding of an atmosphere that itself took an almost unimaginable span of time to build in the first place. To understand how anyone arrives at a number that specific, it helps to return to the quiet chemistry described a little earlier. The rain falling on stone, the carbon slowly dissolving and drifting down toward the sea. That process only tells half the story. Earth's carbon budget has never depended on weathering alone. For every measure of carbon dioxide that rainfall and rock pull out of the sky, something else has always been putting a portion of it back, and that something is fire rising up from deep within the planet itself. Volcanoes, and the slower, less dramatic release of gas along the seams where the planet's crust splits and shifts, have been returning carbon dioxide to the atmosphere for the entire span of Earth's history, a kind of deposit made to balance the withdrawal happening through weathering. Some of that volcanic contribution happens in spectacular, visible fashion, the kind of eruption that makes headlines and draws crowds to a safe distance to watch. But the greater share of it happens far more quietly, along thousands of miles of mid-ocean ridges hidden beneath the sea, where fresh magma rises continuously from the depths of the planet and slowly releases gases as it does, an enormous, largely invisible process that nonetheless keeps pace, in an ordinary era, with a meaningful share of what weathering removes from the sky above. For billions of years, these two processes, one removing carbon, one restoring it, have roughly balanced each other, rising and falling together in a long, patient equilibrium. The ocean itself plays a role in this story too, beyond simply receiving what rivers carry down to it. Seawater holds an enormous quantity of dissolved carbon dioxide, far more than the atmosphere itself contains, cycling gas back and forth across the ocean's surface in a continuous exchange with the air above it. That exchange acts as something of a buffer, a reserve that can, for a time, cushion sudden shifts in atmospheric carbon dioxide by releasing or absorbing gas as conditions change. But a buffer of that kind is not the same as a solution to the underlying trend. Over the kind of enormous timescale this story is concerned with, the ocean's reserve shifts in step with the same slow decline governing the rest of the system, offering patience rather than escape. But the two sides of the weathering versus volcanism balance do not respond to a brightening sun in the same way. As the sun grows warmer, rainfall increases across the planet, and weathering, tied directly to how much rain falls and how warm that rain runs, speeds up in direct response. Volcanic activity answers to an entirely different set of forces: the slow churning of Earth's deep interior, the drift of continents, the rise and fall of mountain building, none of which take any particular notice of how bright the sun happens to be on a given day, a given century, or even a given 100 million years. Picture an old-fashioned balance scale, the kind with two pans hanging from either end of a beam. For most of Earth's history, those two pans, carbon removed by weathering on one side and carbon returned by volcanic activity on the other, have swayed gently around roughly the same level. But only one of those pans is tied to the sun's own steady climb. Weight keeps piling onto it, decade after decade, while the other pan changes at its own unrelated pace. Given enough time, the loaded side wins, and the balance that held for so long slowly, irreversibly, tips. That tipping point matters enormously, because carbon dioxide is not simply a passive gas drifting through Earth's atmosphere. It is, for the overwhelming majority of plant life on this planet, an essential ingredient, every bit as necessary as sunlight or water. The particular chemistry most plants rely on to turn sunlight into sugar, a pathway botanists call carbon-3 photosynthesis, found in the vast majority of trees, grasses, and food crops covering the planet today, requires a minimum concentration of carbon dioxide in the surrounding air simply to function at all. Fall below that minimum, and the process does not merely slow down, it stops working. Scientists do not have to guess entirely at what happens near that threshold, either. Studies of plant growth under artificially lowered carbon dioxide levels, conducted in greenhouses and growth chambers built specifically to test the limits of photosynthesis, along with evidence from Earth's own ice ages, periods when atmospheric carbon dioxide dropped low enough to visibly stress certain plant communities, both point toward the same general threshold used in Ozaki and Reinhardt's calculations. The number is not simply theoretical. It reflects a boundary plants have already brushed up against, in a milder form, within Earth's relatively recent past. Picture an old farm well, the kind dug by hand generations ago, drawing steadily from an underground water table that used to sit close to the surface. For a long time, the well keeps producing, even as the water table drifts lower year after year, because there is still enough depth to reach. But a well like that does not fail gradually, the way a faucet might slowly reduce to a trickle. It works perfectly well, right up until the water table drops below the bottom of the well, and then, quite suddenly, it produces nothing at all. Earth's atmospheric carbon dioxide is behaving in something like the same way, drawn down slowly and steadily by weathering that keeps outpacing its volcanic replacement, still sufficient for photosynthesis today, and for a very long stretch of time to come, right up until it isn't. This is precisely the mechanism Ozaki and Reinhardt built into their model, a slowly brightening sun driving ever more rainfall, ever more weathering, and an ever-declining reservoir of atmospheric carbon dioxide that volcanic activity has no reliable way of topping back up at a matching pace. Somewhere in that long decline sits a threshold, the point at which carbon dioxide finally falls below what the overwhelming majority of Earth's plant life needs to keep photosynthesizing at all. Once photosynthesis falters on that scale, the oxygen it has produced for billions of years no longer gets replenished at anywhere near its current rate, and the atmosphere's oxygen content, the very thing that makes this planet's air so unusual among anything astronomers have found elsewhere, begins its own decline soon after. Running that entire chain of consequences through hundreds of thousands of separate model calculations, each one nudging the uncertain details slightly differently, is how Ozaki and Reinhardt arrived at their answer. A mean estimate of 1,080 million years from now, with a margin of roughly 140 million years on either side. It is worth pausing on that margin for a moment, rather than rushing past it. 140 million years sounds, on its own, like an enormous span of uncertainty, and in absolute terms, it plainly is one. But set against the total figure, it amounts to something closer to 13%, a genuinely tight range for a calculation reaching this far into the future, built on honest science rather than false confidence. To feel the true size of that margin another way, consider what 140 million years actually represents in Earth's more recent history. That span reaches back to the Cretaceous period, when dinosaurs still walked across the surface of this planet, long before anything resembling a primate had ever appeared. The uncertainty surrounding Ozaki and Reinhardt's calculation, in other words, spans roughly the same stretch of time, separating the height of the dinosaurs from the modern world, and their best estimate still lands comfortably within that range on either side. Some of that uncertainty comes from not knowing, with total precision, exactly how quickly certain rocks weather under certain conditions. Some of it comes from uncertainty about the deep interior of the planet, and how much carbon dioxide volcanic activity will continue supplying over such an enormous stretch of time. None of it comes from doubt about the basic mechanism itself, which rests on chemistry and physics about as well understood as anything in modern Earth science. It is fair to ask whether other researchers looking at the same basic problem have arrived at meaningfully different numbers, and the honest answer is that the specific figure Ozaki and Reinhardt calculated represents the most detailed, most comprehensive treatment of the question to date, built by combining biogeochemical modeling with stellar physics in a way earlier studies had not fully attempted. Earlier, simpler estimates of Earth's long-term habitability existed before their work, generally focused on temperature and water rather than oxygen specifically, and those studies pointed toward the same general neighborhood of time, the same rough order of magnitude, without offering the same level of detail about the atmosphere's chemistry itself. Science of this kind rarely produces a single number and then stops. It produces a best current answer, openly built on stated assumptions, ready to be refined the moment better data or a sharper model comes along. When that threshold is finally crossed, The change that follows does not creep forward the way the preceding billion years did. Anyone who has ever tested the ice on a frozen pond in the dead of winter knows this kind of transition instinctively, even without the science behind it. The ice holds and holds and holds, seemingly unbothered by an entire season of gradually dropping temperatures, right up until the exact moment weight and thin ice finally meet the wrong way, and then it gives all at once, with almost no warning between solid and gone. Ozaki and Reinhardt's model shows something structurally similar. The decline of atmospheric oxygen, once the underlying carbon dioxide threshold is crossed, unfolds rapidly by the standards of Earth's history, a comparatively sudden collapse layered on top of a slow, billion-year buildup. Part of what makes this particular transition so abrupt, once it begins, traces back to a feedback loop within the collapse itself. As photosynthesis falters and less new oxygen enters the atmosphere, the natural processes that consume oxygen, various forms of chemical weathering, and the slow respiration of the planet's remaining organisms continue removing it regardless, no longer offset by fresh production at anywhere near the previous rate. The imbalance that results does not simply hold steady at some reduced level. It accelerates its own decline, oxygen production falling as carbon dioxide scarcity deepens, and oxygen levels then falling further still as the biological systems that once helped regulate atmospheric chemistry lose the resources they need to function. Each piece of the system leans on the others, and when enough pieces falter together, the whole structure gives way considerably faster than any single piece declined on its own. What comes out the other side of that collapse is, in its own way, a kind of return. The model finds that atmospheric oxygen falls sharply toward levels last seen on this planet before an event geologists call the Great Oxidation Event, a turning point in Earth's history that unfolded roughly 2.5 billion years ago, when photosynthetic microbes first began pumping enough oxygen into the air to fundamentally change the planet's chemistry. Piecing together that ancient history took geologists the better part of the 20th century, working from clues scattered across ancient rock formations on nearly every continent. Some of the earliest hints came from a peculiar kind of ancient river deposit containing grains of certain minerals that dissolve almost immediately in the presence of oxygen, yet somehow survived intact in rocks older than roughly 2.5 billion years, a preservation that only made sense if the rivers depositing them had been flowing through an atmosphere with little or no free oxygen at all. Additional evidence sits in striped, rust-colored mineral deposits called banded iron formations, layers of iron that only accumulated the way they did because the ocean water surrounding them was still low in oxygen, still able to hold iron in solution the way it can no longer do in today's oxygen-rich seas. None of this relies on guesswork about the deep past either. Scientists reconstruct ancient atmospheric chemistry through several independent lines of physical evidence. The chemical makeup of ancient soils preserved in the rock record, tiny bubbles of genuinely ancient air trapped inside certain minerals, and the ratios of different forms of the same elements locked into rocks that formed at specific, datable moments in Earth's history. These independent methods, developed across different research groups over decades, generally agree with one another about the broad outline of how oxygen and carbon dioxide have shifted across Earth's long history, which is precisely the kind of cross-checked, independently confirmed foundation that makes it possible to trust a model attempting to run that same history forward into the deep future. The far future atmosphere Ozaki and Reinhard describe carries a similar chemical signature to that ancient world. Methane elevated well above today's levels, carbon dioxide scarce, and no meaningful ozone layer at all, since ozone itself is simply a form of oxygen, and an atmosphere without abundant oxygen cannot sustain one. Losing a functioning ozone layer carries its own separate consequence, distinct from the loss of oxygen itself. Ozone high in the atmosphere absorbs a significant portion of the ultraviolet light arriving from the sun before it ever reaches the surface, acting as a shield that has been in place in some form for roughly as long as the atmosphere has held substantial oxygen. Remove that shield, and a much larger share of the sun's ultraviolet output would reach the ground directly. A change with obvious consequences for any surface-dwelling organism, though by that point in the story, complex, sunlight-exposed life of the kind capable of noticing such a thing would already, for entirely separate reasons, no longer be part of the picture. Methane matters here for reasons beyond mere chemistry. Molecule for molecule, methane traps far more heat in an atmosphere than carbon dioxide does, acting as a considerably more potent greenhouse gas over any given stretch of time. An atmosphere that has traded most of its oxygen and carbon dioxide for methane, the way the model describes, would behave very differently from today's air in terms of temperature regulation, layering a distinct, hazy quality over the planet, not unlike what spacecraft have photographed drifting across Titan, Saturn's largest moon, where a thick, methane-rich atmosphere gives the entire world a soft, orange cast from space. Earth's future atmosphere would not resemble Titan's in temperature or overall makeup. Titan sits far colder and holds onto nitrogen as its dominant gas rather than anything resembling Earth's future mix. But the general visual impression, a world wrapped in a hazy, methane-tinted atmosphere, offers a useful, real image to hold onto. It helps to hold onto some sense of scale here, too. Today's atmosphere is roughly 1/5 oxygen, a proportion so essential to how animal life burns fuel and generates energy that even modest deviations from it in either direction have profound effects on living things. If that entire planet-wide reservoir of oxygen were represented by a full swimming pool, the atmosphere Ozaki and Reinhard describe on the far side of the collapse would be represented by roughly a single cupped handful drawn from that same pool, and every so often a good deal less than that. This is not a thinner version of today's air. It is a fundamentally different atmosphere, chemically closer to the world that existed before animals, before forests, before anything resembling the ordinary background of a nature documentary film today. Picture what this looks like on the ground, in the plainest terms available, long before that final threshold arrives. Forests begin thinning at their margins first, the driest, most marginal stands of trees, losing their struggle against a slowly starving atmosphere, while richer, wetter regions hold on longer. Grasslands, many of which already rely on a different, more carbon dioxide efficient form of photosynthesis, better suited to leaner conditions, likely persist longer than forests do, becoming, for a stretch of time, the dominant green covering across a planet that once supported far more variety. Eventually, even that more efficient strategy runs out of room to compensate, and green cover of any kind becomes the exception rather than the rule across most of the land. None of this happens in a single lifetime, or a single century, or even a single million years. It happens the way everything in this story happens, gradually And then, at the very end of that long gradual decline, comparatively fast. This is the point in the story where the language has to be handled with real care, because it is easy to overstate what a figure like this actually means, and just as easy to understate it. Complex, oxygen-breathing life, the kind that depends on pulling enough oxygen from each breath to fuel an active, energy-hungry body, requires atmospheric oxygen levels far above what the collapsed, far future atmosphere would provide. Every land animal alive today, every bird, every mammal, every creature with lungs or gills built around extracting oxygen efficiently from air or water, belongs to a category of life. This transition would not permit to continue, at least not in any form resembling what exists now. What the model does not describe is a dead planet. Life of a different, older kind, the kind that dominated Earth for most of its history before oxygen ever became abundant, could well continue on a world like that. Microbes drawing energy from chemistry that does not require oxygen at all. Methane-producing organisms thriving in exactly the kind of atmosphere the model predicts. In that sense, Earth would remain, technically, a living world for a very long time after the transition described here, quietly hosting the same broad category of life it hosted for roughly the first half of its entire history. Long before anything with a spine or a leaf ever existed, there is something strange, almost quietly unsettling, about that image. A planet still undeniably alive, still cycling energy and chemistry the way living worlds do, and yet a planet that could no longer support anything resembling the audience listening to this sentence right now. Some of the organisms best suited to a world like that already exist today, tucked into environments most people never think to look. The anoxic mud at the bottom of certain lakes, the digestive tracts of grazing animals, hot springs and hydrothermal vents where sunlight never reaches at all. Microbiologists call these organisms methanogens, and they represent some of the oldest lineages of life on the planet, chemically capable of thriving in exactly the kind of oxygen-starved, methane-rich conditions the far future atmosphere would provide. In a strange sense, these overlooked, unglamorous organisms, rarely featured in any nature documentary, may turn out to be far better suited to Earth's long-term future than anything living in a forest or an ocean today. This has real consequences for how scientists think about the search for life among the thousands of planets now known to circle other stars. An oxygen-rich atmosphere is not just a temporary phase in a young or a dying world. It appears to be a temporary phase, full stop, a narrow window bounded on one end by however long it takes photosynthetic life to first accumulate enough oxygen to become detectable across interstellar distances, and bounded on the other end by a collapse very much like the one described here. A distant civilization pointing its own instruments at Earth today would see the telltale signature of a living world. That same civilization, observing this exact planet a little over 1 billion years from now, would see something that, by the oxygen-based standards scientists currently rely on, looks unremarkable, even though life, in some form, would very likely still be quietly present the entire time. This detectability problem does not diminish the value of searching for oxygen elsewhere. If anything, it sharpens the case for looking at as many nearby stars as possible, and for developing methods sensitive enough to detect other kinds of biological signatures beyond oxygen alone, signals that might reveal a living world during the far longer stretches of its history when oxygen is not yet, or no longer, part of the picture. A civilization searching only for worlds that currently look like Earth does today risks missing every planet currently living through its own version of the billion years before the transition, or its own version of the billion years after it, both of which, added together, vastly outnumber the comparatively brief window when a world looks like the one under your feet right now. There is one more detail worth carrying forward from Ozaki and Reinhard's own findings, one that reshapes how the rest of this story should be understood. Their model places this atmospheric collapse before two other major thresholds in Earth's long decline: the point at which rising heat begins driving water vapor into the upper atmosphere in earnest, and the much later point at which the oceans themselves begin slipping away into space. The air, in other words, appears to fail first, on its own separate and considerably shorter timeline, while the water Earth is famous for. The oceans that cover most of this planet's surface, and have done so for billions of years, are governed by an entirely different clock, one that has its own history of scientific debate and revision. Everything explored here, the weathering, the balance scale tipping slowly out of true, the well running dry below the surface, the ice giving way all at once after holding for so long, belongs to the story of Earth's air specifically, a story that, according to the best current science, reaches its own quiet ending roughly 1 billion years from now. But air is only one half of what makes a world like this one livable. That clock and the long, genuinely contested scientific argument over exactly how it ticks is where this story turns next. For now, sit with this alone. The air over your head, the very thing keeping the room around you comfortable enough to drift towards sleep, has a calculated, scientifically defensible expiration date, and that date arrives closer to 1 billion years from tonight than to the 5 billion most people assume, long before the sun ever becomes the swollen ending everyone already thinks they know. Air is only one half of what makes a world like this one livable, and the other half deserves the same careful, patient attention just given to the first. Long after the atmosphere has already lost the fight described earlier, Earth would still, for a very long stretch of time, be covered by its oceans, the same restless blue surface visible from orbit in nearly every photograph ever taken of this planet from space. But that water, too, sits on its own countdown, driven by the very same brightening sun responsible for everything discussed so far, though by an entirely different mechanism, arriving by an entirely different and far more hotly debated timeline. To understand why the oceans have lasted this long despite billions of years of a brightening sun, it helps to understand a quiet piece of atmospheric engineering built entirely by physics rather than by any hand that has been protecting Earth's water for as long as the planet has had an atmosphere worth speaking of. High above the clouds, you can see from the ground, temperatures in Earth's atmosphere drop remarkably cold enough that water vapor rising up from the warm, moist air near the surface runs into an invisible ceiling. Any water vapor reaching that height simply freezes and falls back down before it can climb any higher. Scientists call this layer the cold trap, and it behaves something like an old screen door on a summer porch, built to keep the vast majority of what's outside from ever getting all the way in, even though a determined mosquito or two might occasionally slip past the edges. For most of Earth's history, that cold trap has kept all but a vanishingly small trickle of water vapor from ever reaching the upper atmosphere, where sunlight could break it apart and let its pieces drift off into space. None of this rests on theory alone. Weather balloons and, more recently. An entire fleet of satellites in orbit have spent decades directly measuring the temperature and moisture content of Earth's atmosphere at every altitude, confirming, layer by layer, that the cold trap behaves exactly the way the underlying physics predicts it should. Today's stratosphere really is cold enough, and really does stay dry enough, to keep all but a whisper of water vapor from ever reaching the heights where sunlight could tear it apart. That confirmed, present-day baseline gives climate scientists solid ground to stand on when running the same physics forward across a much brighter, much warmer future. As the sun continues its long, slow climb in brightness, the same climb responsible for everything already described, ocean temperatures eventually rise enough that more water evaporates into the air than the cold trap can comfortably screen out. The stratosphere itself begins to warm, and as it warms, the ceiling that used to hold water vapor back starts letting more and more through, the screen door effect weakening, letting in more than the occasional determined straggler. Climate scientists call this stage the moist greenhouse. The surface remains recognizably Earth-like during this phase, warm and humid rather than obviously scorched, but high in the atmosphere, water vapor is now present in meaningful quantities for the first time, exposed directly to ultraviolet sunlight, strong enough to tear individual water molecules apart into hydrogen and oxygen. Picture what the earlier stages of this process might actually look like, long before anything resembling the scorched world described later on tonight. Coastlines would retreat as rising seas, warmed and expanded by heat rather than by any change in total water volume, push inland across low-lying regions. Storms would grow more intense, feeding on warmer ocean water and a wetter, more energetic atmosphere. Regions that once supported farmland might shift toward the poles, chasing a climate zone that itself keeps sliding away from the equator as the whole planet warms. None of this would be sudden, and none of it would be visible from one year to the next. It would be the kind of change a geologist notices across careful measurements spanning centuries, long before it became the kind of change anyone standing outside on a given afternoon could actually feel. Hydrogen, the lightest of all elements, does not need much encouragement to leave a planet entirely. Once freed from the water molecule that had been holding it, individual hydrogen atoms high in the atmosphere move quickly enough and weigh little enough that many of them simply escape Earth's gravity altogether, drifting off into space and never returning. The oxygen left behind mostly reacts with surface rock and other chemistry rather than escaping in the same way. The net effect, repeated molecule by molecule across enormous stretches of time, is a one-way leak. Every water molecule broken apart high in the atmosphere represents a small, permanent loss from the planet's total water supply, a supply that, unlike carbon dioxide, has no volcanic process capable of meaningfully replacing it. There is a curious postscript to the oxygen left behind once each water molecule breaks apart high in the atmosphere. In the world described earlier tonight, an atmosphere already running low on the free oxygen photosynthesis once provided in such abundance. This new source, arriving from broken up water molecules rather than from any living process, would not remotely make up the difference. The quantities involved are vastly smaller than what photosynthesis produced when it was still operating at full strength, a faint trickle set against what had been, for billions of years, a steady flood. It stands as a small, almost ironic detail, even as water molecules break apart, and release oxygen directly into the sky, the atmosphere, as a whole, would already be moving firmly in the opposite direction, its overall oxygen content falling rather than climbing, driven by the much larger changes described earlier rather than by this comparatively minor side effect. The hydrogen escaping Earth during this process does not simply vanish from the universe, even if it vanishes from Earth's own accounting. It joins an extremely thin, extremely diffuse cloud of particles drifting through the solar system, the same general environment that spacecraft instruments detect streaming outward from the sun itself as the solar wind. Mars offers a preview of what a planet looks like well after most of this kind of loss has already happened. Spacecraft orbiting Mars today have measured its atmosphere still bleeding away into space at a slow but steady rate, and most planetary scientists now believe Mars once held far more water and a far thicker atmosphere than the cold, thin, rust-colored world visible through any telescope tonight would ever suggest on its own. The difference between Mars's fate and the one described here for Earth comes down largely to size and gravity. Mars is smaller than Earth, with correspondingly weaker gravity holding its atmosphere in place, making it considerably easier for that atmosphere to bleed away into space over time. Whether or not any runaway greenhouse process was ever involved, Earth's larger size and stronger gravitational pull make this kind of atmospheric loss far more difficult. One more reason. The timelines discussed tonight stretch into the billions of years rather than the mere hundreds of millions that reshaped a smaller, lighter world like Mars. For years, the standard way scientists modeled this process relied on what are called one-dimensional climate models, mathematical tools that treat the atmosphere as a single vertical column of air, averaged across the entire planet, rising from the surface to space. These models are relatively simple to run and have taught scientists an enormous amount about planetary climates in general. But that simplicity comes at a cost. They cannot represent clouds, weather patterns, or the difference between a humid coastline and a bone-dry desert in the same afternoon. Working from that simpler approach, earlier research suggested Earth could begin slipping into a moist greenhouse in as little as 150 to 170 million years, with a full, unstoppable runaway greenhouse arriving within 600 to 700 million years. After that, a timeline that, if accurate, would have placed the ocean's fate on a schedule not so different from the atmosphere's. None of this, it bears repeating, describes anything remotely close to a human time scale. Even the earlier, more pessimistic calculations placed the first stirrings of a moist greenhouse hundreds of millions of years away, a span of time in which the sun, in the very ordinary, everyday sense that has nothing to do with tonight's story, will simply keep rising and setting exactly as it always has, for longer than any calendar humanity has ever kept, could meaningfully measure. That picture changed substantially once researchers built more sophisticated tools capable of modeling the atmosphere in 3 dimensions rather than one. Tools built to capture clouds, regional weather, and the enormous variation between a rainforest and a desert on the very same planet. 2 scientists in particular, Eric Wolf and Owen Toon, atmospheric researchers at the University of Colorado Boulder, took on the challenge of running Earth's future through exactly this kind of 3-dimensional climate model, the same general category of tool used today to study modern weather and climate change, only pointed forward across a timescale of billions rather than decades. Their results, published in Geophysical Research Letters, a widely respected peer-reviewed journal for atmospheric and climate science, told a strikingly different story than the older, simpler models had. Wolf and Toon tested what would happen to Earth's climate as the sun grew brighter by specific, deliberate amounts, running the planet forward through their three-dimensional model, rather than assuming the outcome in advance. In one especially telling test, they increased the sun's output by roughly 15.5% above today's level and watched what the model predicted. Earth's current global average temperature sits close to 59 degrees Fahrenheit. Under that brighter sun, the model's global average climbed to roughly 104 degrees Fahrenheit, a startling, uncomfortable rise by any measure, and yet the oceans, according to the model, did not boil away. The stratosphere did not warm enough to break the cold trap in any meaningful way. Earth, remarkably, stayed dry up above, even while growing considerably hotter down below. The difference between the two sets of predictions comes down to details the simpler models could never capture. Clouds, it turns out, do a great deal of quiet work, reflecting sunlight back into space and radiating heat away from the planet, work that a single averaged column of air cannot represent. Deserts and other dry regions behave similarly, radiating heat efficiently back into space rather than trapping it the way moist, cloud-covered regions do. A three-dimensional model that can tell the difference between the Sahara at noon and a rainforest canopy at the same moment captures a planet that cools itself more efficiently than the older, averaged approach ever gave it credit for. Wolf and Toon's work found that this extra efficiency buys Earth considerably more time than anyone had previously calculated, roughly 10 times longer before the moist greenhouse threshold arrives, and roughly 3 times longer before a full runaway becomes truly unstoppable. Even Wolf and Toon's own results have continued to be tested and refined by other researchers in the years since, exactly the way healthy science is supposed to work. Some follow-up studies have examined how the specific arrangement of continents and oceans on a given world might shift these numbers further, since a planet covered mostly in ocean behaves differently under a brightening sun than a planet with large, dry, sun-baked continents. Other researchers have explored how clouds specifically made of water droplets, as opposed to other kinds of atmospheric haze, might reflect even more sunlight than accounted for in the original modeling, potentially extending the timeline further still. None of this refinement has overturned the central finding. If anything, the broad direction of that ongoing research keeps pointing the same way. Earth's oceans appear to be considerably more resilient and considerably more patient than the earliest generation of climate models ever gave them credit for. Translated into a concrete timeline, Wolf and Toon's revised estimate places the onset of a moist greenhouse at a minimum of 1.5 billion years from now, a full billion years further out than the older calculations had suggested, and pushes the point of a genuinely unstoppable runaway greenhouse out even further still. There is, however, an important detail worth holding on to once that first threshold finally arrives. The distance between a stable, moist greenhouse and a runaway greenhouse turns out to be considerably narrower than the distance it took to reach the moist greenhouse in the first place. Picture a canoe drifting down a wide, slow river, the current barely noticeable for mile after mile, right up until the river narrows and the water begins to move with real purpose toward a waterfall somewhere ahead. The long, slow drift represents the better part of 1 billion years spent easing toward the moist greenhouse threshold. The narrow, faster stretch just before the falls represents how little additional brightening, roughly 2% more sunlight than what triggers the moist greenhouse itself, is needed to tip the process into a runaway it can no longer reverse. To feel the true size of even this more generous timeline, consider that 1.5 billion years reaches back to a period when the most complex organisms anywhere on Earth were single cells, before anything resembling a plant, an animal, or even a mushroom had ever evolved, back when the most sophisticated life on the entire planet consisted of individual cells that had only just begun developing a nucleus to organize their own genetic material. The distance separating that ancient, almost unrecognizable version of life from the world outside your window tonight is roughly the same distance separating today from the earliest point at which Earth's oceans might conceivably begin their own slow transformation. Add together everything explored so far, and a clearer picture of Earth's total remaining lifetime as a recognizably living, recognizably blue world begins to take shape. The atmosphere holds for roughly 1 billion years. The oceans, more resilient than once believed, appear to hold considerably longer than that, likely well past the 2 billion year mark before any of this reaches its most extreme conclusion. Compared against the roughly 4.5 billion years Earth has already existed, and the 10 billion years or so a star like the Sun spends in its stable, hydrogen-burning phase altogether, the full stretch of time during which this planet looks anything like the world outside your window tonight represents a surprisingly narrow slice of the Sun's total life story. A bright, blue, watered window sitting somewhere in the middle of an otherwise far longer and far less hospitable timeline. There is no need to imagine what the far end of that process looks like, because a real visible example sits close enough to study directly through any reasonably capable backyard telescope. Venus and Earth, formed from largely the same swirling disk of dust and gas, at nearly the same time, from roughly the same raw ingredients, close enough in size that early astronomers assumed the two must have followed similar paths. What set them on such radically different courses was, in the end, not composition or size, but simply distance, a difference of only about 25 million miles in orbital radius, a gap that sounds enormous, stated plainly, but which, in the delicate balance of a planet's total sunlight received, made all the difference between a world that kept its oceans and a world that lost them completely, permanently, and long ago. From space, the two planets could hardly look more different, despite their similar size. Earth appears as a blue marble, swirled with white cloud and green-brown continents, an image made famous by astronauts on their way to and from the moon. Venus, by contrast, appears as a featureless, pale yellow-white sphere, its entire surface permanently hidden beneath an unbroken blanket of cloud that no visible light camera has ever managed to see through. Only radar, capable of passing straight through that cloud cover the way it passes through fog, has ever revealed what the Venusian surface actually looks like. A world of vast volcanic plains, towering mountains taller than anything on Earth, and no oceans, rivers, or lakes anywhere to be found. The surface of Venus today sits at roughly 867 degrees Fahrenheit, hot enough to melt lead outright, and hot enough to make Venus the hottest planet in the entire solar system. Hotter even than Mercury, even though Mercury sits nearly twice as close to that same star. The mechanism responsible for that extreme heat is the greenhouse effect operating at its most extreme, the same basic principle, in a much gentler form that keeps Earth comfortably warm rather than frozen solid. Sunlight passes through a planet's atmosphere and warms the surface below. That surface then tries to radiate the heat back out towards space as infrared energy, but certain gases in the atmosphere carbon dioxide chief among them, absorb a portion of that outgoing heat and send some of it back down toward the surface, rather than letting it escape freely. On Earth, this effect is modest, and without it, this planet would be a frozen, largely lifeless ball, rather than the comfortable world outside your window. On Venus, with an atmosphere composed almost entirely of carbon dioxide and layered dozens of miles deep, that same basic effect operates at an entirely different scale, trapping heat so effectively that the surface below never has any real opportunity to cool. The atmosphere pressing down on that surface is roughly 92 times heavier than the air at sea level on Earth, a crushing weight equivalent to diving roughly half a mile beneath the ocean's surface, made up overwhelmingly of carbon dioxide, wrapped in thick clouds of sulfuric acid that never fully clear. Not a single spacecraft that has ever landed on the Venusian surface has survived for more than a couple of hours before the heat and pressure disabled it completely. The idea of a runaway greenhouse is not a recent invention dreamed up to explain Earth's far future. Scientists first developed the concept seriously in the 1960s, largely to make sense of exactly the kind of puzzling data Venus itself was producing. Early observations from Earth-based telescopes had already hinted that something was deeply wrong with Venus, a planet expected, based on its distance from the Sun alone, to run only modestly warmer than Earth, yet clearly radiating far more heat than sunlight alone could explain. It took a series of robotic missions actually reaching Venus, starting with the Soviet Venera program, which began sending probes toward Venus in the early 1960s, and continuing through NASA's Magellan spacecraft, which spent the early 1990s mapping the planet's surface through its permanent cloud cover, using radar to confirm just how extreme conditions there truly were, and to give the runaway greenhouse concept the observational backbone it needed. Modern spacecraft have added remarkable detail to that early 1960s picture. Magellan mapped roughly 98% of the Venusian surface using radar during its years in orbit, revealing a landscape dominated by volcanic activity, with more volcanoes counted on Venus than on any other planet in the solar system, including Earth. More recent missions, including Japan's Akatsuki spacecraft, have studied the planet's strange, fast-moving atmosphere, where hurricane-force winds circle the entire planet in only a handful of days, even though the solid ground beneath those winds rotates so slowly that a single Venusian day lasts longer than a Venusian year. Whether Venus once held oceans of its own remains one of the more actively debated questions in planetary science, and honesty requires saying so plainly rather than presenting it as settled. Some researchers, working from climate models similar in spirit to the one Wolf and Toon built for Earth, argue that Venus may have supported liquid water on its surface for as long as 2 to 3 billion years after its formation, a world not entirely unlike early Earth, before its own runaway greenhouse finally took hold. Other researchers, working from different assumptions about the young sun's brightness and Venus's early atmosphere, argue the planet may never have cooled enough to hold liquid water at all, remaining too hot from the very beginning. Both camps agree completely on what Venus looks like today. They simply disagree about the path that led there. What matters for tonight's purposes is not which explanation eventually wins that particular scientific argument, but what Venus demonstrates, regardless of how it got there: a rocky, roughly Earth-sized world, orbiting the same sun, can end up exactly where the process described tonight leads, an atmosphere thickened entirely with carbon dioxide, a surface hot enough to melt lead, and not one drop of liquid water anywhere on its face. Venus is not a warning from some other solar system, dreamed up for dramatic effect. It is a next-door neighbor, visible most evenings as the brightest point of light in the sky after the moon, quietly demonstrating an ending. Earth's own oceans are, on some far longer and gentler timeline, already easing toward. This same process reshapes how scientists think about water worlds elsewhere in the galaxy, in a way that closely parallels the concerns raised earlier about oxygen. A planet discovered, orbiting comfortably inside another star's habitable zone, the band of distance where liquid water could exist, is not necessarily a planet that has held on to its water for the planet's entire history. Some worlds currently sitting in that zone may be relatively young versions of a story already familiar from tonight. Oceans intact for now, with a moist greenhouse still billions of years away. Others may be considerably further along, quietly losing their water to space at this very moment, and a small number, orbiting older or more energetic stars, may already have finished the process entirely, leaving behind a rocky, sun-baked world that once, billions of years earlier, looked remarkably like Earth does today. Getting this timeline right carries weight well beyond simple curiosity about Earth's own distant future. Every current effort to catalog potentially habitable worlds around other stars depends, at least in part, on assumptions about how long a planet can be expected to hold onto liquid water once it arrives in a star's habitable zone. A telescope capable of detecting oceans on a distant world, something astronomers are actively working toward with the next generation of space observatories, would still need calculations like the ones described tonight to know whether a given detection represents a young, water-rich world with billions of years still ahead of it, or an older world already deep into its own moist greenhouse, its oceans quietly draining away, even as the light revealing them crosses the vast distance to Earth. It is worth being precise about how these two long countdowns relate to one another, since it would be easy to blur them together into a single vague notion of the future getting worse. The atmosphere's oxygen fails first, on the order of 1 billion years from now, an event driven by carbon dioxide falling too low for photosynthesis to continue at anything like its current scale. The oceans fail later, on an entirely separate mechanism driven by rising heat rather than falling carbon dioxide, with even the most optimistic recent modeling placing that threshold at somewhere north of 1.5 billion years from now, and quite plausibly, a good deal later still. Both processes trace back to the same underlying cause, a sun that has never once stopped growing brighter, but they arrive by different roads, at different times, and would leave behind two very different versions of an increasingly unfamiliar Earth. Everything walked through here, the screen door standing guard high in the atmosphere, the canoe drifting toward a waterfall it cannot yet see, the sun-baked, cloud-wrapped twin next door, offering a preview nobody has to imagine, belongs to water specifically, a slower, gentler, and far less certain countdown than the one governing the air, but a countdown all the same. Between the two of them, air and water, the picture of Earth's habitability comes into fairly complete focus. A planet that keeps its breathable atmosphere for roughly 1 billion years, and keeps at least some meaningful fraction of its oceans considerably longer than that, quite possibly by billions of years more. What neither of these two calculations addresses is the planet itself, the actual rock and iron making up Earth's body, separate from the air wrapped around it and the water resting on its surface. That question belongs to a different kind of physics entirely, one concerned not with chemistry or atmospheric layers, but with orbits, gravity, and the far more dramatic transformation the Sun itself is scheduled to undergo once its own long, stable chapter finally comes to a close. That transformation and the surprising, only recently settled uncertainty over exactly what it means for the ground beneath your feet is where this story turns next, and where the ending most people already think they know finally gets the closer look it has been waiting for all along. Everything explored so far in this story, the air failing first, the oceans following after, both driven by nothing more dramatic than a star doing exactly what stars do, has left one question conspicuously unanswered. What happens to the rock itself? Not the atmosphere wrapped around it, not the water resting on its surface, but the actual body of the planet, the iron core and stone crust that would, in principle, continue existing long after anything resembling today's Earth had already faded into memory. That question finally brings this story to the ending most people already believe they know, and to a genuine scientific surprise, recent enough that, until just weeks before this very telling, the answer would have been given with far more confidence than it can be given tonight. To reach that ending honestly, it helps to return briefly to where this entire story began. A star quietly burning hydrogen in its core, a stage astronomers call the main sequence, one the Sun has occupied for roughly 9.5 billion years combined, past and future, out of a total stellar lifetime that eventually comes to a close. Roughly 5 billion years from now, give or take, the hydrogen fuel at the very center of the Sun will finally run low enough that the delicate balance holding the star steady, the outward push of fusion resisting the inward pull of gravity, can no longer be maintained the way it has been for the entire span of Earth's existence. What follows is one of the more dramatic transformations in all of stellar physics, even though it unfolds slowly enough that no single year would ever look different from the one before it. With fusion no longer providing enough outward pressure, the Sun's core begins to contract under its own weight, growing hotter and denser as it shrinks. That contracting core radiates enormous energy outward, and the Sun's outer layers respond by doing something that seems almost contradictory. They expand dramatically, even as the core beneath them squeezes tighter. The surface cools as it spreads outward, shifting from today's familiar yellow-white toward a deep, smoldering orange-red, the same general color visible tonight in aging giant stars scattered across the sky. This is the beginning of what astronomers call the red giant branch, the chapter of stellar life that gives the whole popular image of Earth's ending its name. Each of these late life stages, unlike the almost incomprehensibly long main sequence that came before them, unfolds comparatively quickly by stellar standards. The red giant branch phase is expected to last somewhere on the order of several 100 million years. The calmer horizontal branch stage that follows is briefer still, and the final, unstable asymptotic giant branch phase, the one that sheds the Sun's outer layers into a planetary nebula, wraps up in a period closer to a few million years. A dramatic finale, playing out over a timescale that would have seemed impossibly long by any human measure, and yet counts as remarkably brief when set against the 9.5 billion years the Sun will have already spent quietly, burning hydrogen before any of it begins. By the time the Sun reaches the peak of this phase, its outer surface will have swollen to something on the order of 100 times its current width, transforming a star that once fit comfortably within a small fraction of Earth's orbit into an object vast enough to reach out toward the orbit Mercury occupies today. Mercury's fate in all of this carries little genuine debate among scientists. Sitting closest to the Sun of any planet, well within the reach of that expanding surface under essentially every model anyone has run, Mercury is expected to be swallowed outright, its rocky surface consumed by the very star it has orbited faithfully for over 4 billion years. Venus fares only slightly better in most calculations, and slightly is a generous word for it. Sitting at roughly 2/3 of Earth's distance from the Sun, Venus sits close enough that even the most optimistic recent modeling still expects it to be pulled into the Sun's outer layers before the process runs its course, a final, almost unbearably fitting end for a planet already discussed tonight as the clearest local example of where a runaway greenhouse leads. Whatever oceans Venus may or may not have held billions of years earlier, whatever the honest scientific debate over its own distant past, its ending appears settled in a way few other questions in this story are. Swallowed by the very star it once, quite possibly, orbited as a living world, Earth's fate and Mars's fate alongside it has never been settled quite so easily, and the reason comes down to a genuine tug-of-war between two forces pulling in opposite directions. On one side sits gravity's tidal pull, the same broad family of forces that raises ocean tides on Earth today, except turned up to an entirely different scale. When a planet orbits close enough to a swollen giant star, that star's gravity can raise a kind of bulge inside the planet's own structure, and friction from that bulge slowly bleeds energy out of the planet's orbit, dragging it, over time, closer and closer to the star. Pulling in the opposite direction sits the Sun's own mass loss. As the Sun sheds a significant portion of its outer material into space through powerful stellar winds during these late stages, its total gravitational pull weakens, and planets orbiting it drift outward in response. The way a skater spinning with arms outstretched slows down and widens their circle as those arms extend further out. For much of the past 2 decades, the leading calculations in this field pointed toward tidal drag winning that contest. A particularly influential study published in 2008, led by astronomers Schroeder and Smith, modeled the Sun's evolution in detail and concluded that Earth's orbit, even after accounting for the outward push from solar mass loss, would not widen quickly enough to escape the pull of tidal drag, and that Earth would ultimately be dragged into the Sun's outer atmosphere and destroyed. That conclusion became something close to a default assumption across popular science writing and documentary storytelling alike for years afterward, repeated so often that it hardened into the kind of fact nobody thought to question further. None of this uncertainty is new to planetary science, even if the specific numbers keep being refined. Astronomers have understood, in general terms, for the better part of a century, that a star like the Sun would eventually swell dramatically near the end of its life, based on stellar physics developed steadily from the 1920s onward, as scientists came to understand how stars generate energy in the first place. What has changed over time is not the broad outline, but the precision, decade after decade, of improved stellar models, better computing power, and, most recently, entirely new physics, describing how energy moves and dissipates inside a star's turbulent outer layers, each refinement sharpening the picture without ever fundamentally overturning the basic sequence: hydrogen exhaustion, expansion, helium ignition. further expansion, and eventual collapse into a white dwarf. Between that original 2008 study and this year's revision, other researchers continued probing the same question from different angles, some finding scenarios where Earth narrowly escapes, others finding scenarios where it does not. The field, as a whole, trending back and forth, without ever fully settling the matter. What makes the newest work notable is not that it is the first to suggest survival, but that it does so using considerably more rigorous first principles physics for the tidal side of the calculations specifically. The piece of the puzzle earlier studies had been forced to approximate more crudely. That default assumption did not hold up once a new generation of researchers looked again, this time with far more sophisticated tools for modeling exactly how tidal energy dissipates inside a giant star. In work published just this year in Astronomy and Astrophysics, a leading peer-reviewed journal in the field, astrophysicist Mats Esselders and colleagues at KU Leuven in Belgium recalculated the tidal side of that old tug-of-war using updated physics developed over the past decade and a half. Physics the earlier 2008 study simply did not have access to. What they found reversed the long-standing assumption. Tidal energy, it turns out, does not dissipate inside a giant star nearly as efficiently as the older calculations had assumed, meaning the tidal brake pulling planets inward is considerably weaker than previously believed. With that tidal brake weaker than assumed, the outward push from the Sun's own mass loss gains real ground in the contest. Enough that current calculations suggest Earth's orbit may widen fast enough to stay ahead of the pull, dragging it inward, allowing the planet to drift into a wider, safer orbit rather than being swallowed. Mars benefits from this same shift even more clearly. Sitting roughly twice as far from the Sun as Earth does, Mars was already considered a reasonably strong candidate for survival under the older assumptions, and the updated calculations only strengthen that expectation, suggesting Mars, too, likely drifts safely outward as the Sun sheds its mass. Mars deserves a slightly closer look of its own, if only because its story so closely mirrors Earth's, offset by roughly one full step further from danger. Everything discussed already tonight regarding Earth's own atmosphere and water applies to Mars in modified form as well, except that Mars, smaller and already far along its own path toward atmospheric loss, billions of years before any of this begins, has little meaningful atmosphere or surface water left to lose by the time the Sun even starts this final transformation. Whatever the tug-of-war between tidal drag and mass loss ultimately decides for the red planet, it will most likely be deciding the fate of a world that was already cold, thin-aired, and essentially lifeless long before the question became relevant. A quiet reminder that not every planet's ending needs a dramatic final act to already be, for all practical purposes, over. None of this should be mistaken for a settled, final answer, and the researchers behind this new work are notably careful on exactly that point. Their own results depend heavily on two specific assumptions: precisely how much mass the Sun sheds during its most active late-life phase, and precisely how efficiently tidal energy dissipates inside a star's swollen, turbulent outer layers, both of which remain areas of active research with real, honestly acknowledged uncertainty. Change either assumption enough, and the outcome can shift back toward engulfment. What has genuinely changed is not a final verdict, but the balance of the argument itself, tipping, for the first time in nearly 2 decades, back toward the possibility that Earth survives, rather than treating its destruction as the safe default assumption. Future research will likely keep sharpening this particular picture rather than closing the book on it entirely. Improved stellar models, more powerful computing capable of simulating the turbulent physics inside a dying star in ever finer detail, and continued observations of other stars currently passing through these same late life stages elsewhere in the galaxy will all keep feeding back into calculations like the one described tonight. It is entirely possible that a study published 5 or 10 years from now revises this picture yet again in either direction. That is not a weakness in the science. It is simply how honest science about genuinely difficult questions is supposed to keep working. It is worth pausing, too, on how unusual it is for any single piece of this kind of storytelling to include a finding this recent. Most of what has been discussed tonight rests on research conducted years, sometimes decades, ago, tested and retested until it earned the kind of quiet confidence that lets a documentary state it plainly. The newest chapter of Earth's story, the one concerning its bare rock, comes instead from research still fresh enough that the broader scientific community has barely begun the years-long process of testing, challenging, and either confirming or revising it. A reminder that the picture of the universe presented on any given night is always, in some small corner, still being actively written. Even setting all of that uncertainty aside, even granting Earth the most optimistic possible outcome in this particular tug-of-war, there is a detail buried within the very same research that keeps this from ever feeling like genuinely good news. The same study that finds Earth's orbit likely widening enough to escape the Sun's outer layers is explicit that Earth's surface, by the time any of this actually happens, would already be entirely hostile to life, scorched by billions of years of a sun that never once stopped growing brighter, exactly the process explored earlier tonight, long before the sun ever needed to physically swallow the planet at all. Surviving the engulfment and surviving as a living world turn out to be two entirely different questions, and this newest research only ever answers the first one. The sun's own transformation does not stop at the peak of the red giant branch either. Eventually, the core, having contracted and heated for long enough, reaches a temperature sufficient to ignite a new kind of fusion entirely, one that burns helium rather than hydrogen, releasing energy in a sudden, brief surge that astronomers call the helium flash. Following that ignition, the sun settles into a somewhat smaller, somewhat calmer configuration for a time, a stage sometimes called the horizontal branch. Before its available helium, fuel eventually runs low in turn, sending the star back into an even more extreme phase of expansion known as the asymptotic giant branch, larger still than anything reached during the earlier red giant phase, and considerably more unstable. During this final, unstable chapter, the sun sheds material into space at a dramatically increased rate, driven by powerful stellar winds and a series of thermal pulses that make the star's outer layers swell and shudder repeatedly. Over time, the sun loses well over a third of its total mass this way, blowing its own outer atmosphere gradually off into the surrounding darkness. What remains, once this process finally finishes, is one of the more beautiful sights in all of astronomy. A planetary nebula, a glowing shell of gas expanding slowly outward, lit from within by the small, intensely hot stellar core left behind at its center. The night sky already holds many examples of exactly this kind of formation, delicate, colorful structures like the Ring Nebula or the Helix Nebula, each one the visible remains of a star that once lived through precisely the same sequence the Sun itself is destined to follow. Some planetary nebulae display delicate, layered shells, evidence of multiple distinct pulses of mass loss occurring in sequence rather than one single event. Each shell, a kind of frozen snapshot of the star's final turbulent years. The Sun's own planetary nebula, whenever it eventually forms, will likely show this same kind of layered structure, a final, glowing portrait built from the last handful of million years of a 9.5 billion year life. At the very center of that expanding shell, all that remains of the Sun itself, is an object astronomers call a white dwarf, an incredibly dense, slowly cooling ember roughly the size of Earth, containing something like half the Sun's original mass, packed into a sphere barely wider than the planet it once warmed. No further fusion takes place inside a white dwarf. It simply radiates away the heat left over from its former life, cooling almost imperceptibly slowly, over a stretch of time so long that not a single white dwarf anywhere in the universe has yet had time to cool down completely, even the very oldest examples known, dating back to the earliest generations of stars in the galaxy's history. If Earth truly does escape being swallowed during the turbulent phases preceding this final state, its ultimate fate would be to spend the remainder of its existence orbiting not the warm, familiar star that gave it life, but this small, cooling ember, a fraction of its former size and light, radiating only a faint glow across a solar system already emptied of Mercury and Venus, its surface long since transformed beyond any resemblance to the world outside your window tonight. Whatever atmosphere might theoretically cling to such a world would receive only a small fraction of the warmth it once knew. The white dwarf's total light output, measured in a tiny percentage of the Sun's present brightness, radiating from an object no larger than the planet it illuminates. Any sky above that surviving Earth would show a small, brilliant point of white light, rather than the broad, warm disk familiar tonight, more akin to an extraordinarily bright star than to a sun in any traditional sense, casting long, cold shadows across a landscape that bears no resemblance whatsoever to anything alive. It is a strange kind of survival, technically accurate and yet almost beside the point, the planet's body persisting while everything that ever made it recognizable as Earth has already, by that point, been gone for billions of years. None of the three thresholds walked through tonight: the failing air, the fading water, the uncertain rock, arrived at through guesswork or dramatic license. Each one traces back to specific researchers, specific published calculations, specific institutions willing to run a model hundreds of thousands of times or recalculate decades-old physics from scratch, simply to answer a question no one alive today will ever see resolved firsthand. That, too, is worth sitting with for a moment. An entire body of careful, patient science devoted to a future no one conducting it will live to witness, undertaken anyway, because understanding a thing fully has always mattered on its own terms, independent of whether anyone will be present to see it confirmed. With that, every piece of tonight's story finally sits together in order, and it is worth laying that order out plainly, one final time, before this telling comes to its close. The air goes first, roughly 1 billion years from now, as a carbon dioxide-starved atmosphere loses the oxygen that has defined it for roughly the last 2.5 billion years. The oceans go next, on a slower, gentler, and still debated timeline, likely beginning somewhere past 1.5 billion years from now, and stretching on considerably further still. And the rock itself, the actual planet, faces its reckoning last of all, somewhere around 5 billion years from now, with its precise outcome swallowed entirely or set adrift around a dying ember, still genuinely unresolved even by the scientists working on the question today. None of this was ever really a story about a single ending, however tempting it had to reach for one dramatic, final image. It was always a story about a sequence. 3 separate, overlapping endings arriving on 3 separate timelines, each one erasing a different piece of what makes a planet like this one worth calling home. Most people, asked to picture Earth's death, reach immediately for the last of those 3, the swollen, dramatic sun consuming the planet whole, precisely because it is the most cinematic, the easiest to hold in the mind as a single image. But it was never the operative threat. It was simply the last chapter of a book whose earlier chapters, quieter and far sooner, were always going to matter more. Perhaps the more useful way to hold on to everything explored tonight is this. Habitability was never a fixed state. A planet simply achieves and then keeps. The way a house, once built, simply continues standing until something knocks it down. It is closer to a narrow, temporary overlap between several separate conditions: breathable air, liquid water, tolerable warmth, each with its own expiration date, each ticking down on its own schedule, briefly and imperfectly aligned for a stretch of time that, on the scale of the universe, barely counts as a moment at all. Every thread of tonight's story, the air, the water, and now the rock itself, has kept circling back to the same broader question: what does it actually take to recognize a living world from a distance, and how long does any given signal of that life actually last? Telescopes currently operating, and others still being planned and built, spend enormous effort attempting exactly this kind of detection around other stars, searching for oxygen, for water vapor, for any chemical fingerprint suggesting something alive might be present. Tonight's story suggests those efforts need to account for something easy to overlook. A planet is not simply alive or dead. It moves through a whole sequence of increasingly quiet, increasingly diminished states on its way from one to the other, and catching a world at exactly the right moment to recognize it as home may be rarer than anyone searching the sky has fully appreciated. Picture, for a moment, that same distant observer imagined earlier tonight, some civilization on some other world, pointing its instruments at this solar system across an unimaginable stretch of space and time, patient enough to check back again every so often across the billions of years ahead. Look today, and they would see a blue, oxygen-rich world, unmistakably alive by any reasonable standard. Look again, a little over 1 billion years from now, and the signature changes entirely. Air gone strange and thin, the telltale oxygen signal that once marked this planet as living quietly vanished. Look again further still, and the blue fades too, replaced eventually by cloud, then by something closer to Venus's own pale, featureless glare. Look one final time, 5 billion years on, and they would find, at most, a small rocky body drifting around a dim, cooling ember, indistinguishable at a glance from any other dead world in the galaxy. Each snapshot would tell a completely different story about the very same planet, and only one of those snapshots, the one happening to occur right now, would show anything resembling a home. There have been, and will be, plenty of other ordinary nights in Earth's long history, Nights when the air was breathable, and the oceans were full, and the sun rose steady and reliable the next morning, exactly as it does tonight. Most of those nights passed without anyone or anything present to notice them at all, across the billions of years before life grew complex enough to wonder about its own circumstances, and most of the nights still to come, across the billions of years ahead, will likely pass the same way, air and water intact for a long while yet, but with the particular species capable of calculating any of this having long since come and gone. The overlap between a habitable Earth and a listening, wondering mind turns out to be its own separate, narrower window nested inside the larger one, and tonight happens to sit inside both. Which brings this story back, finally, to the world outside your window tonight, and to the plain, unremarkable fact of existing exactly when you happen to exist. Every single condition required for a night like this one: breathable air, liquid water, a star still burning steadily, rather than swelling toward its own ending, currently overlaps, all at once, on this particular planet, at this particular moment, a coincidence of timing so specific that it has never happened before across the entire 4.5 billion year history of this world, and will not last forever going forward. That is not a cause for alarm. Every calculation walked through tonight places every threshold discussed comfortably beyond any span of time relevant to a single human life or 1,000 human lives, laid end to end. It is simply a fact worth sitting with honestly. This ordinary night, this particular window of air and water and warmth, is not a permanent feature of this planet. It is a temporary alignment. Currently, quietly, still holding, there was never going to be a single dramatic day when Earth simply died. There was only ever this, a long, patient sequence of thresholds, each one arriving quietly, each one already calculated by careful people willing to do the arithmetic, and a narrow temporary window still open tonight, still holding everything it needs to hold for now. Rest now. Tonight's sky is still yours to sleep beneath.